So okay, so today we are going to cover these support vector machines. Where is this file again? Here. We're going to cover support vector machines, and by now you are familiar with things like supervised and unsupervised. So I don't think it's necessary to go into any detail about supervised learning. Basically, you have some data which has labels, and you use the label data to train the algorithm, then you predict on a test set. So the basic idea is the following. We have a set of points in we can talk of that in a d-dimensional space. So d dimension simply means the number of variables. So there are d variables being measured, and they're all real numbers in this case. So the question is, how do we determine the hyperplane for the decision boundary? So the assumption is that you have at least two classes. In this, the initial case will work with two classes. So the points are all listed here, and they are labeled according to their classes. There's one class here and another two classes. The second class is here. So clearly the data is linearly separable. It's possible to draw a straight line which perfectly separates the data. The question is, what is the best line you can use? That is what we're going to figure out. So as you can see here, all these three lines work. So the question is, which line is the best? Any one of those lines perfectly classifies each data point. But which one, how do we figure out which one is the best? So that's the basic idea. We'll have, here we have used the two-dimensional case to illustrate this, but more often than not, you'll work in much higher dimensions. But higher dimensions are harder to draw. So when you work with higher dimensions now, you'll no longer talk about a line or a separating line. You'll talk about a hyperplane. I don't know if you covered hyperplanes in linear algebra. Did you cover?
No, we did cover hyperplanes.
So you have no idea. Basically, think of it as a line. If you're in 3 dimensions, it's just a plane. If you are in higher dimensions, it's the equivalent, though you can't draw, but you can try to imagine it as a flat plane in higher dimensions, separating two classes. So it's easy to draw in 2 and 3 dimensions. In 3 dimensions, it will be a plane, just the normal plane that you know, and then in 2 dimensions, it's a line. If you work in 1 dimension, if all the points are on a line, then it's just a point. We'll see this later. Okay, so that makes it, the mathematics will look very confusing if you don't know what a hyperplane is. But I'll try to explain. So we try to, the target eventually is we'll try to pick the hyperplane, which has the largest distance to both classes. So among these 3, for example, the one that appears to have the largest distance to both classes, not to just one class, is this L2. This other one seems to be very close to the blue points, but has a larger point, a larger distance to the x's, right? This line 1 is a bit too far from this one and very close to this. So if it's too close, anytime if you have some noise in your data, it could easily be misclassified on the wrong side. It's too close. But you have one that is equidistant. I mean, for it to be farthest from both sides, it has to be equidistant from both. We shall see how that how we come to that conclusion later. But basically, L2 is sort of the best because it's the farthest from both. These others are closer. The L3 is closer to the blue points and farther away from the X's, the black points. So this is what we shall be looking for, this kind of line that separates the two classes, and then we'll be able to classify the points once we know that line. So this is the same idea, but now once we determine this hyperplane that separates the points, we'll want to have a margin around it, and we want to maximize that margin. So this continuous line is a decision boundary. It's the one used to determine whether the points belong to one group or the other. So if they're on this side, they belong to these circles. If they're on the other side, they belong to the blue X marks. So we need a margin that is as wide as possible around the decision boundary, and we also need the margins to be as far the farthest possible from the decision boundary to both sides, not to just one side. So what that means is then the margin must be equal in both directions. So the maximizing the margin is good because it will make sure that if some points, if there's some noise, you still have some allowance for correct predictions. So if some points measurement is bad and somehow they cross the margin, they may not cross too far, and it will still be possible to correctly classify them. Am I making sense so far? You can hear me?
Yes, we can hear you.
Okay. So we've now just discussed why the margin must be as large as possible. It also makes the problem easier to solve. So this is where the problem begins. So I'll try to explain using, so this is, let me try to use the normal. So you're familiar with this, someone is making noise. The equation of a straight line.
Yes.
Usually this,
Yes.
It's mx plus c. Or let's just use b since we're using b anyway. So the points that satisfy the line will satisfy this. The points that are on the decision boundary, if this is your decision boundary, then they will satisfy this. But then you'll have other points that don't satisfy this. There's one set of points that will be greater than mx plus b, sorry. There'll be another set of points that also will be on the other side of a line. So this is the simplest case you can have. So one set of points will be, so in this case, if you write y, if you rewrite this, you'll have y minus mx okay, it will run out of space there, then we won't be able to write. Let me use it here. So if you write the first one, for instance, you'll have y minus mx minus b is greater than 0. The second one will yield a similar result, but now will be less than 0. So all points that satisfy this first set of equation, this first equation will be classified as one class, and the points that satisfy this second set of this second inequality will be put in the second class. So, but this should be, I believe you this should not be hard for you to figure out. You did linear programming in high school at some point, and you normally determine you have inequalities, and you have to determine regions that are satisfy the inequality and so on, things like that. So that's what this line does. So like this first, the first inequality may pick points that are on one side. The second inequality may pick the points that are on the other side. That is just similar to what you did in linear programming in high school. And for those who did linear programming in at the university also, this should be in operations research. You may have done that as well. So that's what all this is talking about. So that's this sign thing refers to greater than 0, that those will be given the negative sign, sorry, the positive sign, and those that are less than 0 will be given negative sign. So the label that we shall use for those that are satisfy this first equation is positive 1. So these ones will be labeled what's going on? So these ones will be labeled. Okay. Just hold on. I'm not used to this writing on the PDF. It's bringing other things that I. So anyway, the label will be 1 for this, positive ones, and negative 1 for the others. So let's delete this. So the assumptions we make are as follows. So this will be a linear equation. So it will be a linear classifier, but we make the following assumption that later on we shall look at something more, some people may call it pathological, but something more, slightly more complicated or more realistic. But to begin with, we'll assume that it's possible to perfectly separate the two classes using a hyperplane. And these coefficients, W is a vector, will satisfy this. They'll be put in canonical form so that any point from your data set, the inner product of that point and this vector W plus B, if you take the magnitude, should be greater than or equal to 1. So this means what this condition simply means is that all your points will be, there will be no points within the margin. If all points are greater than or equal, satisfy this inequality, it means there'll be no points in the margin. So that means the perfect separation works. So I'll just scroll back. You can see, like in this case, all the points are either on or outside the margin. There are no points that lie in here. So that's our initial assumption. It's not always the case, but we'll work with that for now. So the question is how to determine the margin. So all this is talking about the hyperplane. I will avoid the math, but the margin we shall represent it using this letter O, the Greek letter. So this is the margin, and it's the one we want to maximize. So that will be the margin, this distance. So to maximize it, we, after a little manipulation, it's possible to show that this margin is actually equal to 1 divided by the magnitude or the norm of this vector W. So the other thing I will say about the vector W, without going to details, is that the vector W is actually perpendicular to the hyperplane or the line, the decision boundary, which is linear. So a hyperplane for that matter. So this is just a vector that is it's unknown initially. We shall have to determine it to satisfy the given conditions, but it will be perpendicular to the hyperplane. Even from the definition of the separating plane, this vector must be perpendicular. So what follows is a proof to show that this margin is determined by 1 divided by the magnitude or the norm of the vector W. So this is just a description for the margin. That's how you compute it. So since you want to maximize it, we can turn it into an optimization problem and state it as follows. Again, here there's a lot of linear algebra and inner products. If I go through that, I don't think we'll. Is it something I should go through, or maybe assuming that you won't understand and skipping it? Is anything appearing on the screen making sense? Like these symbols, these brackets, these angle brackets, and so on. For inner products. Are you familiar with inner products at all? You can hear me?
Yes, we can hear you.
So what is the answer to the question? You are familiar with this or not?
I think we are familiar with inner product, but in this context, I think you will elaborate so that we probably understand. Yeah, but we are familiar with the inner product.
So how are you representing? Okay, so ideally, what you have is this. It's the following kind. If you work with two dimensions, you'll have something like this. You'll have A1, a coefficient times X. Okay, I need space, so I'll have to start from. I'll have to start from here so that you see it properly. So if you are writing a straight line, you need two variables. So we'll just use x1 as our first variable. Then you'll need a second coefficient. Let's call it a2. You need x2 as your second variable. So this is just the equation of a straight line. This you're familiar with, plus a constant is equal to 0. So that's how you write the equation of a straight line, right? So you can write this first part as a dot product, right? So this first part you can write as a dot product. So you need the vector a1 and a2. Usually you represent them as columns, but I'll just write them as row vectors for now. So this this is a vector containing the coefficients a1 and a2. Then you'll have another vector containing the coordinates of the point x1 and x2. So x1 and x2. So this first part can be written in this form, right? You are familiar with this dot product?
Yes.
Yeah, and then plus the constant. I'll just put the constant here, plus the constant, all this is equal to 0. So this is the equation of a straight line. So how do you write this? This is the same as, now this set of coefficients is what you call W as your vector. And this point is what you call the vector X. So this inner product here is what you are representing as, you put the angle brackets, put W, then a comma, then you put X. So this inner product is just this expression here, if you want to expand it. So this can be extended to more than 2 variables. If you have n variables, you'll have n coefficients. So this vector will have n entries, and also you'll have n entries for for this. So this one assumes your data is living in R2, the two-dimensional Euclidean space. So is this making sense? So you remember the decision boundary initially, if you're working in 2 dimensions, is just a line. So the points on the line, let me delete this now. So the points on the line so your equation will be this. You have a line, that's your hyperplane. It doesn't have to go through the origin. So it could have an intercept different from the origin, but in this case, I've used the origin. So you have some points on that side, and you have the other points on the other side. They can be more. I've just drawn those two on each side. So the points along here are the ones that satisfy this equation. The points here. The points on this side will satisfy, I think will be classified as the positives. If you are to use this as your equation, the points on this side will always give a positive value, and the ones on this side will give a negative value. So these ones are the ones that will be classified as +1, labeled rather as +1, and these ones as -1 in your data. So and then the ones that are on the margins, you see there'll be margins. The whole thing will be rescaled so that the ones on the margin will satisfy. This equation is equal to either plus or -1. So another way of writing this is that the absolute value of this should be equal to 1. And all other points will satisfy the other inequality we set up earlier, that the absolute value would be greater than or 1, greater than or equal to 1. So this usually works better if it's a physical class, because it's able to interact and know whether people are following. What I'm working with here should be familiar to all of you. This is just basic working with coordinates and straight lines. So this at least this should be familiar to you. This should not be strange. So I don't know if that has helped to. So this is now just general way you do it, to write the equation of a straight line, or in the case of higher dimensions, a hyperplane. B will always be a constant. This W will be the vector that is perpendicular to B, to the hyperplane, and then X will be a point on the hyperplane. Any point on the hyperplane will satisfy this equation, and that hyperplane is our decision boundary to determine whether a point is on one side or the other. So now still, I don't know whether that answers your question about explaining further. Is that making sense?
Yes, I think I can now follow. Yeah.
Yes. So, but this simple example is not the one you should focus on, because you will rarely work in 2 dimensions. You need to think in this general sense. This is more general than the one we are working with. So this whole procedure, I will avoid it, because since you are not familiar with a lot of these things, like norms and inner products and so on, this whole thing is trying to show us why the margin should be this. That's the proposition we set up earlier. So this one proves that the margin will be given by 1 over the norm of W. The norm is just the length of a vector. So once you establish that the margin should be given by 1 over a norm of W, we can set up an optimization problem to find the correct value of W and B, the constant B. So like I said earlier, we want the margin to be as wide as possible. And secondly, we assume that all points are correctly classified. So there are no points inside the margin. All points are outside the margins. So that means all points are correctly classified and outside the margins. There are no points inside the margin. So these are the two things we need to consider when doing the maximization. So what we need to maximize therefore is the margin, which is this. That's 1 over the norm of W, subject to these conditions. Now, there's a new variable here which has been introduced. So this one simply checks whether this is a classification variable, which is either plus or minus 1. Plus to mean you are in one group, minus 1 to mean you're in the other group. So yi is just a classification with a grouping variable. That's what has been introduced. We defined it earlier though. And then this second assumption, as I said earlier, tells you that there are no points inside the margin. They're either on or outside the margin. So if you have to draw your margin, so that was a decision boundary. And this is the margin on that side, and there's a margin on that side. Then all points are either here, or maybe on the margin. There are no points inside here. So it means the classification will be perfect. This boundary will give you a perfect classification in that case. So, but it's easier, instead of maximizing 1 over the norm, it's easier to just minimize the norm itself. And even easier to minimize the square of the norm. Because if you minimize the square of the norm, it's the same as minimizing the norm. So instead of working with this minimization problem, you now shift to this one. So this becomes your new minimization problem. And this is the classification variable that I mentioned earlier. It makes them one group is labeled as +1, the other one is labeled as -1, depending on whether they satisfy one of these inequalities. So this problem is called the primal hard margin problem. The reason it's called hard margin is because the margin is quite this margin does nothing crosses the margin. It's a hard margin, so there are no points inside the margin. But this does not always work. There are situations where you will find most of the data you encounter will not have a perfect, will not be linearly perfectly linearly separable. So that will only work if your data is perfectly linearly separable. So outside that, we can consider a second situation where we allow for some misclassification. So the points will not be perfectly classified. There may be some errors. Some points may lie on the wrong side or on the wrong side of the margin, but we still want to do some classification. We are willing to live with that error and still proceed to do some classification. So to do that, we have to rewrite the optimization to add some term here. These are the slack variables we add. This will allow us to we'll now take care of the fact that there are some points that will drop inside the margin and some will be misclassified, which is more realistic. So when you add these slack variables, the optimization now has to happen with these new constraints. This penalty term, I think it's called this Greek letter is called what? Eta. I think it's eta. I need to double check the name of the Greek letter. So for each term, there's a penalty. So those that are correctly classified, the penalty will be 0. Those that are not, that are within the margin will have some non-zero penalty, and those that are misclassified also will have some penalty. And this epsilon is a value that is, this eta is a value that is non-negative. It is not, it can't be negative. this penalty, and it's different for each point. Each point will have its own value calculated. So that simply means this will run from 1 up to the total number of points, assuming that your sample, you have n observations, not n observations, n observations. The variables we agreed are d, since we are working in the d-dimensional Euclidean space, so you have d variables. But now the number of points you have will be n. So for each of those points, you need a separate error. So in total, this vector over which you're minimizing will have n points, each of them labeled as E1, eta 1 up to eta n. So this becomes your new optimization problem, where you don't have a perfect linear separation between the two classes. So these parameters, you will have to tune them to get the ones that give you the best results. So the things you have to get are this vector W and this constant B, as well as these etas, eta 1 up to eta n. I think someone is trying to join. Let me check. I've had yes, so I've admitted the ones who wanted to join. So anyway, so basically that's the point. We have two cases: the hard margin, where there are no errors in prediction or rather in classification. Every point is perfectly classified. Then there's this soft margin example where we allow some errors. But all this will be done for you by the computer. Now you're just trying to understand what the model says. We don't seem to have enough time. So how to solve this? You'd have to use Lagrange multipliers to solve these optimization problems. I don't know if you remember Lagrange multipliers from calculus. In any case, I don't think we have enough time to go through the details of Lagrange multipliers, but that's what you will need to solve this. You will have to set up the dual problem. There's something to be learned from the optimization process. Eventually you end up showing that the solution only requires the inner product of the points. That's all you require to find the solution. So when you are solving the problem using Lagrange multipliers, that's what you end up with, which finally leads to what we normally call the kernels. In this case, you use a linear kernel, but while working with that problem or solving this problem, you can show that especially if now the decision boundary is not linear, then you can use some kernels to separate to determine the decision boundary. So the kernel simply, you push the whole space into a higher dimensional space. In the higher dimensional space, most likely you'll be able to linearly separate the points. Once you separate the points in the higher dimensional space, you can be able to bring them back in the original space. So the boundary would be linear in the higher dimensional space, but non-linear in the original space. We will see some examples in the code as we go along. So that's basically the idea. The rest is just tells you what happens for different values of this penalty term. For this soft margin. So what we have done, the hard margin, there are no errors in classification. Soft margin, there might be some possible errors, which is a more realistic case. And for that, you add some slack variables and the constraint also changes to this. So you have the slack variable plus the constraint. So I don't know whether it's necessary to go through the solution of this optimization problem. If we do, I don't think we'll do anything else in the class. That is all we shall do for the class for today. If we try to solve it. So maybe I can write out the, later on I can write out the, solution and give it to you. It will not be examinable, but some of the maths diehards may want to know it. So does this make sense? It doesn't have to make complete sense because you not implement this manually. You just need to get the overall picture. So I need to know if it's making sense. You're not very willing to speak. So this one talks about the loss function, and it's based on these constraints that comes from the soft margin optimization problem, and the loss function will it's actually a hinge loss. The hinge loss function, hinge because it's like this. So for points that are correctly classified, the loss is 0. And the ones that are in the margin, within the margin also the loss, there's some loss, non-zero. But as you go further and further away from the margin, the loss increases linearly. So the loss keeps increasing as you go further and further away from the margin. So this is normally called the hinge loss. I don't know if you have covered any other loss functions.
Yes, we have covered some other loss functions.
Yeah, so you know what this is, the hinge loss.
But we have not covered the hinge loss, other loss functions apart from the hinge loss.
So you have covered the
root mean squared error.
Root mean squared error, and
we have also covered
another logistic loss.
Yeah, the seal hoot. Yeah.
Okay. Anyway, that is fancy stuff to know. Most of it is done by the computer for you, so it may not be necessary to go into details about the loss function. But it's important to understand the bigger picture of this. You may not need to calculate all this, but at least you should be able to set up the optimization problem as written here. The derivation of all this optimization problem is included in the notes. The only problem is you don't know what a hyperplane is. So that is a big problem actually. If you don't know what the hyperplane is, it's difficult to follow. Unless everything is reduced to the two-dimensional space, then you'll simply be working with a straight line, and that will beat the purpose of doing a master's if you reduce everything to 2 dimensions. But anyway, I hope the coding will bring the madness to an end. So there's some method to the madness. It will become clear shortly once we do the coding. So I need to stop sharing this so that I can share my screen. So I'll bring up the R Studio. Again, the code was done in R. Python also has in this sklearn package, I think there's it's much easier to run it in Python. The setup in Python is a little better than, or rather, I think it's a little better to run, easier to run than, although it gives you a lot of black box stuff. You don't see a lot happening. It hides a lot of stuff from you, but it's much easier to set up. But I have not done it in Python. You can try to do it in Python on your own. We shall just do this in R. The one thing that maybe we might, if we do it, we'll have to do it in Python is the neural networks. I think that should be our next topic. I've started working on the notes. I think this is a correct file. So what we'll start with is a one-dimensional case. So we simply have a one-dimensional data set. One dimension simply means 1 measurement for each case. In this case, it's just some sugar content that is measured on some soft drinks. So if you view the data, this is what the data will look like. These are just sugar measurements of sugar content in some soft drinks. So this is done for about 25 of them. So you want to know whether you can classify these soft drinks based on the sugar content, or if there are any. Once we are now going to plot what is in the. Once we plot it, you can display the plot. You can see my R screen. Eh?
Yes.
Yeah. So you can see there seems to be two separate types of drinks. So these ones, sugar content is between 7.4 and 8.9. This one, the sugar content is 10 and higher. So they seem to be two groups. So if you want to separate this, you will need a margin. Here, the margin will just be a point since we are working in one dimension. So margin is just a point here. Everything is on one line. So the margin will just be a point. So your best margin will be the one that is equally between these 2 points, 8.9 and 10. So it will be somewhere in between here. Let's generate it. The one that is perfectly halfway between the 2 points is here. Then we'll plot it. So now it has been plotted. This is the margin. And then these ones will be on the boundary. So this is the decision boundary, and the margins will be here. One will be here, and the other one here. So that distance here is the margin. So now, if anything is on that side, it will be classified as this class of soft drinks, and anything measuring on that side will be classified as this class of soft drinks. So that's the simplest possible case you can encounter. And this becomes your decision boundary. So if you get a new soft drink, measure the sugar content and see on which side it lies and then classify it. So you can maybe call these ones soft drinks A, and this one's B. Whatever class you choose to give them. So we try out the two-dimensional case. So in this case, we'll set the seed so that you get the same results as what I get. So we'll generate some set of points in 2 dimensions. So we'll have a set of points that maybe will serve as the X coordinates and another set of points that will serve as the Y coordinates, right? So this will generate a set of X and Y values. We'll use this uniform distribution. We generate random numbers which are uniformly distributed. And the interval is between 0 and 1. And we want n of them. We already set n to be 600. So we are just generating 600 of them here. And another set of 600 to represent the Y coordinates. So that one has been. So let's view the data. The data frame after we have generated it. View DF. So here are the points now. We have points. If you are to use the standard notation for 2 dimensions, usually just have X and Y. But for linear algebra, we prefer to use these indices to label the variables. So X1 and X2, those are our variables. So we are going to create a line to classify the data. So the line we shall create, or in this case, the hyperplane, is the line y minus 1.4x is equal to 0. So in this case, we choose B to be 0. Okay. So if the points lie, if any points on this line are less than 0, any points for this function here, this linear function, if the value is less than 0, they will be labeled -1. And if they are greater than 0, they'll be labeled 1. So we'll add a new variable, which you call small y, which labels the points depending on which side of this, or which side they lie of this hyperplane. So think of this as just a line. You will see it anyway in a minute. So we are going to, let me run this and you will see the plot. So if you plot this, the points will be split, but there will be no margin between them. So we'll create a small margin to separate the points. So the margin is this 0.07. So we go back to our data frame and only retain the points that are outside the margin. So this code here simply picks out the points that are outside the margin. So now when you plot the data, you will see that we plotted the margins as well. You will see that we can use a hard margin here to classify. The data is perfectly separable. So this one we are basically simulating. We are rigging the data. We have not started running the support vector machines. We are working on an ideal case by creating it. So here you have the margins. This code here draws the margins as well as a decision boundary. But now you can clearly see we have kicked out all the points that are in. If you are to plot this, you can see this ggplot. You plot df. If you are to plot it before, before it was converted, it was higher up. I don't want to mix this. So if you are to plot it before kicking out everything in the margin, So I'm just going to plot that right now. Yeah, x is equal to x2, and color was what, y. Yeah. Then we do a scatter plot of this before we remove the points in the margin. Let's just check. Oh, this second one should be y, not x. So if you draw that now, you can see what they look like. So there's a straight line here. This line that we have here, y minus 1.4x is equal to 0. You can't see the line, but it's the one that marks the boundary between the 2 points. So the points that lie on one side are labeled red. The other ones are labeled, are colored blue. It's blue or green, I don't know what the color is. So, but we don't want this kind of thing. We want to remove some of the points here so that we can have a hard margin and clearly separate the two groups, right? So this is basically what you are doing in linear programming in high school, finding regions of feasibility and so on. So this is one region for one inequality. This is another region for the same equation, but the opposite inequality. Okay. So this is what it would look like before you remove. So we are going to rig this by removing some of the data. We have the decision boundary there. We'll create a margin and remove some of the data. And then when we do that, the plot now looks like this. Then we draw the margins as well. So this is the kind of setup we have. We have two groups. One group is on this side, the other one is on that side. That's the decision boundary, and these are the margins. So this is the hard margin where there are no points inside there. So support vector machines now can classify this. So we'll use the linear SVM. Later on, we shall look at a situation where the decision boundary is not linear, but you can still push the points into a higher dimensional space where they can be separated by a hyperplane. For now, let's stick to the simple case. We'll split this data set, the one that has been where we have cleared the points within the margin. So we're going to split this data set into the training set and the test set. That's what is happening here. I believe you'll be able to understand the code. Do I have to explain every line? Because there's nothing spectacular happening there. It's just the standard R code. If you have been working with R, it should be familiar. But since you're not the one who wrote it, you just may need to spend a bit of time to look at it. It should make sense. Is this making sense so far? It's important that you talk. It's quite hard to get words out of you.
It's making sense.
Oh, okay.
Yeah.
So we already split it into the training, and we are doing it manually. The other way is to split it using functions, but I think you know those other ways. So this one is doing it manually makes you understand better. So there's this library, this E1071 is the one that has this algorithm for the support vector machine. So we are going to apply it to the data. So we had a classification variable which we called y. It took the values either 1 or -1, depending on which side of the decision boundary the values lie. So the data is already labeled. We have to specify the data. In this case, we are using the training set. We have to specify some more things like type. So we'll use this C classification. I think there's one more option for this. I can't remember what it was. But remember when we were doing the soft margin case, there's a point where we used the constant C, right? So this C is the same constant in the optimization problem that we set up. Now we shall work with the linear boundary. So we'll take the kernel to be linear. Later on, you can specify a different kind of kernel here, depending on the kind of decision boundary you think might be there. So this is sort of the vanilla kind of application for SVM. We don't do any data processing. In some cases, you may need to preprocess your data by scaling. In this case, we choose not to scale, right? So we will not scale in this case. We keep that option as false. Scale is false. So we are basically trying to look for a linear decision boundary to classify the data. So I have run the SVM model. You can check the kind of things that the model has. It has many, I don't even know all of them myself, but our interest is things like kernel. Gamma is useful, I think, when you're working with the radial basis. Kernel. Epsilon, I think when you're doing optimization, some of these, we might use some additional parameters here. I don't know all of these, but there are some that will be able to get you the support vectors and so on. So this command just gives you all the possible components. You can extract the ones you want. So if you want to get the indices of the support vectors, this is the attribute you will use, the capital S and V. The model is still the same one we generated up here. Use this attribute to get the support vectors, to get the index or the indices of the support vectors. That's the attribute you use. To get the y-intercept, this is a row. Let's just run all this and see what we get. So we have gotten all of them now. The first one gives us the support vectors. Now, the support vectors are simply the vectors that are either within the margin or they are misclassified. So the support vectors are the ones that are within the margin or they are misclassified. It turns out that the reason they're called support vectors is that if you only have the support vectors, then it will generate the same parameters for your model. You don't need the other points to generate the parameters for the model. It's only the support vectors that count. So the points that are on the margin, within the margin, on the margin, and misclassified, those ones are what we call the support vectors. Once you have those, you can even ignore all the other points in trying to solve the optimization problem. So I think that's the genesis of the name support vectors, support vector machines. So we can do some prediction. This command predict, you give it the model that you trained. Let's do the prediction on the same training set and see what happens. You can see the accuracy is 1. So it's perfect because the decision boundary is exact, so it's perfect. So we remember we had split it earlier into training and testing set. So again, it turns out that on the testing set, we have perfect prediction. So this is not a surprise because we rigged the data to begin with. We made it have a perfect linear separation. And we expect the accuracy to be 1 because the separation is perfect. You can't misclassify any point under these circumstances. Is that making sense? So one run of accuracy, of course, is not sufficient to come to a conclusion. You need to do some cross validation. We'll do that in a later example. Is that making sense?
Yes, yes, it's making sense.
Okay. So already, because the nodes are built for teaching this, I keep including some of these commands, but like now ggplot is 2 is already loaded, so I don't need to run this again. So you may see this a lot as you go along. There are a lot of repeated commands, but it's because it's built for teaching. If you're running it on your own, and so this is for convenience. So if I choose to start from here, then I do not have to go back and look for the point where it was loaded. If I close the thing and I start from here, I don't have to go back up to look for it. But when you're doing actual work, you probably will load all the libraries you need at the top before you proceed. So we can visualize this, the model that we've run. Already we have, this is a rigged one. This is the one we created. So we want to see what will happen if we use the one that is determined by the. So this was the training set. Let's just plot the training set, the points in the training set, and we color them using the actual labels from the data. So we have stored that in this scatter plot. Then on this plot, we are going to add a few more things. We will add the support vectors. To find the support vectors, you need the indices of the support vectors, and you use the indices to extract them from the training set. Right? So your data here, we just pick the training set and do a scatter plot of the training set, support vectors only. And then we're going to color them purple and make them bigger. Okay, have I run this? So in this case, we have drawn now, these are the support vectors. These points in here. These are the ones that fall within the margin. But they're still correctly classified because they all fall on the correct side of a decision boundary. But they're the ones that will fall within the margin that was computed by. Yeah. So you can add a decision boundary based on the coefficients that you get from the running the support vector machine algorithm. You can, this is all these things is simply calculating the slopes and so on to be able to, and intercepts for the decision boundary and the margins. And so after that, you can plot them. And then you will have that. So the support vectors are the ones that are in either on the margin or within the margins. In this case, we are lucky the support vectors are also correctly classified because they fall on the correct side of the decision boundary. So here the classification for support vectors is fine. And this is what you would call the, what do they call it? The hard margin. It's a bit of a soft margin because we still have some vectors inside the margin, but none of them is misclassified because the hard margin does not allow any vectors in the margin. So this is soft. It's a soft margin.
I have a question.
Yes.
So in this case, sorry, when you are, so how does the model identify the decision boundary? sorry, I have a sword. Okay, are you guiding it somewhere? Like you're telling it this is where you to draw the, or is it just like it trains and understands this is how the data is and it decides this is where I need to put the decision boundary? Maybe I missed that. How does it come up with that?
When we're doing the theory, we needed to pick out this vector of coefficients, right? The W1, the W vector. So there's an algorithm that runs within R. Once you run this command, this SVM command, let's go up and you'll see this SVM. Once you run it,
yes,
the same way you learn a linear regression model, you just give it whatever information it needs, then it will spit out the details that you want, right? So we looked at the things that it spits out. That's the names of the output, the things that it, so it has all these things. We don't need all of them. We may be interested in things like the cost. I think this is the value of that constant C. Later on, when dealing with the nonlinear decision boundaries with the Gaussian kernel, I think we may need this value gamma. The kernel has to be specified. It's, in this case, we are looking for a linear decision boundary, so the kernel will be specified as linear and so on. So these are specifications you need to make. If you're doing, if the kernel is of degree of some, if a polynomial of some degree, then you have to specify the degree and so on. So it does all that for you. Here I'm trying now to extract the coefficients. So you don't need to know all these things. I'm showing you how to extract them so that you can connect them to what we are doing in the notes. I don't know if this is making sense.
Yeah, it does. Thank you. So somehow the model goes like, okay, there's a, how do you say? So,
it will not draw these lines for you, but it will give you the information you need to draw the line. So I'm using that information from the model without having to go back to the mathematics.
Okay.
So you have to take this as the gospel truth. So to find the slope for your line, this is a slope. It gives a slope. You can find the intercept and so on.
I see.
So they have the same slope. All the lines have the same slope, but you can see you have to remember the margin. The size of margin was 1 over the magnitude of W. So this one gives you the size of the margin. So if you subtract the margin from the intercept, you will move the line you get will still be parallel to the decision boundary, but it's moved up. Then I think one moves up, the other one moves down. When you add, I think it goes up. When you subtract, it goes down. So you get these two lines and you just draw them. That's all. Once you have their slopes and the intercepts. But if the one you need initially is a slope and intercept of the decision boundary, once you have that, you subtract the margin from the decision boundary and also add to the decision boundary to get these two margins, these lines, the intercepts for the margin lines. Then this command draw up line usually draws a line. Given once you give it a slope and the intercept, it will draw the line with that, a straight line with that slope and that intercept, y-intercept. You are familiar with this geometry for ggplot? Yeah. You give it a slope and the intercept, it will draw that line. So the algorithm will not draw this for you. You will have to extract this information the way I've done it and draw it here. But this is when you're doing analysis, you will not need to do this. You probably will have to. You'll be more interested in other things other than the diagram. Most of the time, you'll not even be able to draw this because you'll not be working in 2 dimensions. So this is supposed to be. This is more like some way to visualize what we are doing in the theory. So that's what makes you a data scientist. You should be able to do this in the background. This is not something you'll go to show your manager or the CEO. You will not care about this, but this is something you will care about in your own small community as a data scientist. So I don't know if I've answered your question.
Yes, you have. Thank you. Yeah, I think you said the model is somehow trains itself and understand these boundaries. Like there's a black, how do you say, this hole that it doesn't, we can't really see. There's a mathematics behind it, because I was wondering, like, how does it know that, okay, that line is not supposed to move up or down? Like that's really where the is making the decision boundaries to be.
So it simply runs the optimization.
Okay.
The same optimization problem we set up in the theory is the same one that is now solved by the algorithm. Then it gives you all the parameters that you need.
Okay, thank you.
You can't do it manually. These points are too many, because it has to, you could also choose to program it from scratch, but there's no point. There's already an algorithm existing.
Okay, thanks.
But if you want to program it from scratch now, you have to go back and understand those inner products. You must understand the hyperplanes, all those things. You must now go back into the theory. So this just illustrates what we were doing earlier. So now we've been able to do a situation where you have perfect linear separation. So again, this library is already loaded. I don't have to load it now. So let's run this model again. Although we already ran it, but I'm just running it afresh. Then we can now plot the model. And then plot it on the training set. So this is what it does automatically. If you may not like this, but this is what it does automatically. So the ones that are labeled as X's, the ones labeled as X's are, is someone's microphone on? No. So the ones that are labeled as X's are the support vectors. You can see these ones labeled as X's. They are the ones within the margin. So this is the one that is given to you directly by R. If you don't want to go into the hard work of, I believe this one looked neater, more presentable. This one we did manually, but if you want to do it automatically, you just plot the model and specify the training data. Where is it? Then it will do everything for you. So the margins are not plotted, but you can see they will be just around here where the X's end, and there will be another margin somewhere here. So the X's will be within the margins. Those are the support vectors. So some of these parameters, like when you're working with a soft margin, you have to add this parameter C, right? And that is called the cost. I think the default value is 1. The default value for the cost is usually 1, but if you run the model with just that cost, let's see what happens to the margins. So we create another one where the cost is now 100. Then that's the model. So the difference is the following. You have for the one where the cost is 1, I think the margins are much wider. So you have a lot of support vectors. So you normally don't want to have too many support vectors. So the cost sometimes can help you reduce the number of, adjusting the cost can help you reduce the number of support vectors. So the higher the cost, the fewer support vectors you have. So we don't know whether 1 or 100 is the best. You would have to tune it properly to get the optimal value. So we will do this. We will add decision boundaries. Again, we want them on the same plot. So what have I done here? So now this one will plot the margins again. We've done that here. So this plots the margin for when the cost is 1. So I think we can do the same, but now plot the margins with a new cost of 100. So observe these margins, they contain way more vectors. Now when you reduce when you increase the cost, C, there are fewer support vectors. You can see, I think we counted 6. You might be able to count them here. 1, 2, the ones that are either on the margin or within. There's 3, there's 4, there's 5. I think 6 somewhere there. So they are fewer. When you have a higher cost, you have fewer support vectors, and then you have a better model. We will see how to tune that later. This was just to illustrate that switching the cost, the value of the cost, changes the model. So ideally, this support vector machines is set for is set up for binary classification where you have 2 classes, but it's possible to extend it to more than 2 classes. So here is an example. I don't remember how many classes were in this. We have a test set and a training set for, I think, a data set that has 3. Let's view it. I think it has 3 labels, 3 different labels. Let's just view the data and then we'll know what is in there. Yeah, so it has 0, -1, and it also has 1. So it has 3 labels instead of 2. So this still works if you run it for 3. So we'll run the model on that data. Remember, you need to use the grouping variable. In this case, it was Y, the one that gives you the labels. And then you run it. Since we need all the other variables, the reason we don't specify them explicitly, we just put the dot. It will assume this is all the other variables in the file will be used now in the model. I think you're familiar with this notation for the formulas, where you use the dot to indicate that you're using all the remaining variables for the model.
Yes, we're familiar with it.
Okay. So we run the model and try to do some prediction, and let's see. It has a good prediction for the training set. Let's see what happened to the test set. It's about 98%, not too different. So now let's plot this one that has, so what you see, it has 3 classes. So we need 2 decision boundaries. So one group is here, the other group will be here, and the other one will be here. So, but the ideal case is where you work with 2 classes. If you have more than 1 class, then it can be extended. but most of the time it's built for 2 classes. So this is a classification. We have seen the kind of accuracy that we got from there, because the data was rigged also. It's rigged to have 3 boundaries. So it's contained in these text files. There are these 2 files, the train set. I will send all this to you, the folder that contains these data files as well as the code. So there's no big difference in how you run it. You run it the same way you would do for whether they are multiple classes or just 2 classes. It's the same idea. Then you can predict and get the accuracy and so on. So I think all of you are familiar with how to obtain the accuracy using this mean function. Do you see why this will give you the accuracy, this mean?
No, not for me.
So it's only you.
I don't know, but it's not clear for me.
But you kept quiet. Why didn't you shout? You should have thrown 1 stone at least. Let me see if I can. So basically the following, this is what will happen. You compare the predictions for the test and the actual labels, right? So this will give you a logical vector with true or false values, right? At least that part you understand. You're comparing 2 vectors of the same length. So where they agree, it will give you the value true, and where they don't agree, it will give you false. Right?
Yeah.
So so but when you try to get the mean, it will treat this as a numerical vector of 0s and 1s. Right? So if you get the mean of a numerical vector, it will simply get the total number of 1s over the length of the vector. So the total number of 1s is where the vectors agree. They agree with each other.
See. So it treats the true and false as numerical values?
Yes.
Okay, yeah, that's what I didn't understand. Okay.
So I hope it makes sense to everyone.
Yeah, that's clear to me.
Yeah. Okay. You probably will encounter this again when you are looking at other, what do you call it? Other scripts that other people have written. So it's quite common to use this to compute the accuracy. So, but this is better when you do it this way. You understand things. You know exactly what is happening. You have packages that can actually throw out all these things for you. But since this is class and you want to be data scientists, it's basically it's good to understand to go into the mud, basically. So here we've plotted the classification, and you can see the boundaries and everything. So you are familiar with this Irish dataset, which has I think 3 different types of species for the iris flower. And then there are some measurements on 150. I think they usually 150, what do you call them? Samples from different flowers, 50 of each type. There's a good chance you have worked with this data set. So now we are going to use cross-validation to create a better measure rather than just doing one run for accuracy. So we're going to run this 100 times. Then each time we pick a different training set and a different test set. So randomly we pick a training set, and then the remaining bit will be the test set. So we want 80% of the data. So sample size will about 80% of it. and that will be the training set, then 20% will be the test set. That's what this first part does. So, but this is going to happen 100 times, right? And each time that happens, we update this accuracy. We start with an empty vector for accuracy, and we keep updating it every time we run. So the accuracy will run 100 times, and each time we record the accuracy for that run into this vector called accuracy. So I don't know if the loop makes sense. We start by initializing the vector that will contain the accuracy, split the data into a training and testing set randomly. So every time you'll get a new training set and a new testing set. Run the model, compute the accuracy for that run, store that accuracy in this vector. Is that making sense? It's just
yes, it's making sense, yes.
Okay. So I will run this. Okay, I have not run the top one first. So now it's fine. We can quickly see the first 15 values of the accuracy. So we are trying to predict the values for the flowers. So these are the first 15 runs, and each of them is quite good. In some cases, we have perfect prediction. Some cases not, but quite high, generally higher than 93% most of the time. So we can get the average for this and see if they deviate by a lot. So the average we get is 96% accuracy for the 100 runs. And the deviation is quite small. It's plus or minus 0.03 if you want to work with one standard deviation away from the mean. So the error is not too big. It's really small, 0.03 standard deviation. So this is a better measure than just running the accuracy once and then forgetting about it. So there are algorithms, I think you may have come across them by now, that will do this cross-validation for you. But now this one is better because you get to construct it yourself and you understand what is happening in cross-validation. So there's the other type of validation where you split the data into blocks and run the training on all the other blocks, test on one block. The k-fold cross-validation. So that was not of big interest for this class. This class was actually we were more interested in optimization, but it's just that we have a problem with the math background, so that we can't go deep into optimization. So we are forced to go back into this prediction or predictive analytics instead of focusing on the optimization. But I think everyone will be happy at the end of the day, hopefully. So are there any questions on this?
Yes, Dr. I have a question.
Yes.
I've seen all along we've been using the accuracy as the loss function, or just to determine how the model has performed in our predictions.
Yes. Yeah.
What about the one that you mentioned at first, the Hing loss, something like that?
No, I have not coded that. It will, if you wish, we can organize for a separate class for that.
Okay, so does it, okay, my question then is, when presented with such a model, do we use accurate?
But the hinge loss simply tests, it's a loss for each point.
Okay.
That's the one used in the optimization bit. So it will tell you whether your point is correctly classified, whether it's within the margins, or
Yes.
whether it's wrongly classified.
Okay.
So if you want to check the points that are wrongly classified, you don't need the hinge loss. You can always check your confusion matrix.
Okay.
You know how to set up the confusion matrix?
Yes.
So if you want to see the ones that are misclassified, you simply set up your confusion matrix. You will be able to find them.
Okay.
But the hinge loss, you will rarely need to compute that when you are doing this analysis. It's more on the understanding the theory side of generating the coefficients, the coefficients for the vector, or the generating the vector W and the constant B. You don't need it so much when you're doing the analysis. So I don't know if your question is well answered or.
Yes, the question is well answered.
Yeah, so now the next thing we have is you can have a situation where, let me see if I can get a board. I will share the code again later. Let me see if I can share the whiteboard. I need to illustrate something. So it's loading the whiteboard. If you can see it, there was someone in the waiting room. If anyone says they're in the waiting room, please let me know. Once I move to the slide, I can't see. So this is what we had last time. It's still there. I'll just delete it. So sometimes, where are the pens again? Yeah. You can have a situation like this where the decision boundary is not linear. So we have some points here. They be more than 2, of course, but to save time, I'll just draw 2. Then the other points maybe are on this side. So the boundary may not be. Let me extend this. So the decision boundary that separates the two classes may not be linear, right? Maybe something like a polynomial. So in this case, if you try to apply the linear kernel directly, it doesn't give a very good, the prediction will be really bad, right? But clearly there's a boundary, it's just not linear. So what happens in such a case, sometimes you will need some function which shifts this to a higher dimensional space. And in the higher dimensional space, it may turn out that the boundary will be linear. You'll have a hyperplane. So now you will run the SVM, the linear SVM in the higher dimensions. And once you find the linear decision boundary, you can map it back to the original data and be able to determine the boundary, which is not linear. So that's basically the next bit. So that's where now the concept of the kernels come in. I did not explain it in the theory because it's actually a lot of work explaining this kernel. If you are to do it properly, there's a lot of work involved. I think I can still write the notes for it and share. It's also available in your textbook, the one I shared. The details about the kernel, but you will not understand it if you don't know what hyperplanes are and so on. It's possible to get a rough definition of what the kernel is, but it's not very helpful, the rough definition. But I think you get the point now. Here, sometimes the boundary that separates the two classes is not linear, but you still want to use a support vector machine. So what you do is you transform it into a higher space using some function. Sometimes they prefer to use this phi to represent the function. And in this higher space now, the points may be linearly separable. Sometimes it may not even be a higher dimensional space. It can still be the same two-dimensional space. But still, the transformation makes the boundary linear, and then you're able to apply the algorithm for the support vector machines. Okay, so let me share the R again. So that's what we are trying to do now, to work with cases where the decision boundary is not so it may be useful to plot this data for the iris if you want to visualize it. It's actually possible. You can view the data file and plot it, and then try to see where they fall in this. You could plot this kind of thing. We didn't plot it for iris, but you can try to plot it yourself and see where the decision boundaries are. You should have three of them, three classes, so two decision boundaries, so that you can split the three classes. So now, if the decision boundary is not linear, it may be some polynomial. We again will start with some data that is rigged, so that we actually know the exact boundary that exists, and then we try to recover it using support vector machines using a polynomial kernel. So we shall set the boundary to be a polynomial. So we need to generate about 400 points, pairs of points. So that's what I've done, and put them in a data frame. So we have two variables, x1 and x2. Each of them has 100 measurements to give us pairs. Now we want to separate the points using a circle of radius 0.8. So some points will be inside the circle, others will be outside the circle. So the decision boundary will be circular. So we need the square of a radius to set up the circle. So this is just geometry. What this next one is doing is it's classifying the points. The points that are outside that small circle will be labeled 1. The ones that are within the circle will be labeled -1, and they'll be colored differently. Then when we plot, this is what they look like. So we actually have set up a circular boundary and split the 2 points. So the decision boundary is a circle centered somewhere here of radius 8. Centered at the origin, actually, and of radius 8. It doesn't have to be centered at the origin, but even if it is not, it's always possible to shift everything to the origin. So it's sufficient to study it at the origin. So you can see now this, we have two groups. So these red ones represents one group, one class. The blue ones is another class. But now we have a problem. The decision boundary is not linear. It's actually a circle. We know what it is exactly because we created it up here. It's actually a circle of radius 0.8 centered at the origin. So how do we handle this? I will split the data into two, the training set and the testing set. So 80% will be the training and 20% will be the test set. So that's what happens there. Then I will run the SVM model, but now there's one more. Okay, before we change the kernel to polynomial, let's see what happens if you try to use a linear kernel to classify this. So we'll run the SVM model with a linear kernel, and let's see the prediction on the test. So now you can see the prediction is no longer good here. It's about 63%, the accuracy. But this again is just one run. If you want to, so you might even tune the parameters. Initially, we kept the cost parameter at 1. Let's see what happens. Does it help if you try to tune the parameters? Again, if you tune the cost to 100, which one have I just run? Doesn't improve, right? And the training, in fact, the training is 53, and on the test set it's a little higher, but not so good. So you can see trying to use a linear kernel, or assuming that these two classes are linearly separable, does not yield good results. So you might think that maybe, oh, it was just one run. Let's see what happens if you do this 100 times. So we create an empty, we initialize the accuracy, then run this 100 times, with a linear kernel 100 times, and we try to see what the accuracy looks like. Again, you can see the average accuracy is still low, about 55%, and the standard deviation is 0.04. But it's still low, the accuracy is low. Standard deviation may not be so bad. It doesn't vary that much, but it's consistently low. So that means assuming a linear kernel is bad for this kind of thing. So we can revisit the same data. So here we are redoing the data because, like I said, sometimes you want to start, if you're teaching, you may want to start from somewhere in the middle, which forces you to reproduce some of the data. So I'll just reproduce the same data and then transform the data So let me go back. I think I need to explain this. Let me go back to the board, the whiteboard. So I'll try to explain this. So the decision boundary was a circle. So it will be something like x squared plus y squared is equal to, in our case, it was 0.8. So you can turn this into a linear in some sense by calling x squared x and calling y squared, say, capital Y. So now this looks like a linear decision boundary. So you do this transformation and treat the squares of the values as your value for x and the squares of the values of the variable y as values for this capital Y. When you do that now, you know, the decision boundary is no longer quadratic, it is now linear. So when you do that transformation, in this case, we have not moved out of the two-dimensional space. We are still in the two-dimensional space, but in some cases, you may need to go to a higher dimensional space to be able to separate the data. In this case, we are lucky we didn't have to change the space. After that transformation, when you plot the data, you will see that now they are linearly separable. You can see that now. Is this making sense? So we basically transformed the data.
I'm not sure why do we need to transform? Sorry, like when we want to do.
So you can see the previous plot, the boundary was circular. So you can't use the linear SVM here. But when you apply the kernel, you transform the data so that in the new space, you see even the arrangement is different. It's the same data but transformed. So that now the two classes are linearly separable.
Yeah, okay, yeah. So that I see. Now the points.
So now you can run the SVM on this because you know that now your data is linearly separable, and then once you get this boundary using this transformed data, you can always take it back to the original space, and in the original space now it will be a circle. You can transform it back to original space.
Okay. Yes.
But this is done for you. This one is manual so that you see what happens with an example. But most of this work is done for you by the model. And in any case, you will not know the boundaries when you. Sometimes you may not know the boundaries very well. They may not be very clear because you'll be working with high dimensional data which you cannot plot. I interrupted you a lot, so I don't know if you are satisfied with the answer.
No, that makes sense. No, I think it's clear. Thanks.
Okay. So instead of doing all that manual work, you can just specify the kernel instead of linear. You specify the kernel as polynomial, then you run the SVM, and it will try to find. In this case, we know the polynomial was degree 2, so we specify the degree to be 2. Anytime you specify the polynomial kernel, you must specify the degree. If this doesn't work, you can try higher degrees and see if that works. So we run the SVM model and check the accuracy again on the test set. Now the accuracy is quite good because we have changed the kernel. You see, previously we tried running this with a what do you call it? With a linear kernel, we're assuming the decision boundary is linear. Didn't go very well. So when we change the kernel to polynomial, it will do the transformation under the hood for us. We specify the degree, and if we got the degree right, then.
Sorry, are you sharing your R studio? I can
no,
see.
I don't think so. Let me. Okay. I forgot to switch. Thank you for that. If you notice, I'm not sharing. It's good to. It's good to let me know. Thank you. Now you can see the R studio.
Yes, thanks.
So this was the original data where we had put a circular boundary or a quadratic boundary. It's a polynomial of degree 2. We have, I think you saw this case where we transformed and now we had data that's linearly separable. That was manual. So now let's see how if for you to do it automatically, you run the same SVM model on the data, but you specify the kernel to be polynomial because your decision boundary was a polynomial, and we knew it to be a polynomial of degree 2. So we make those specifications. And when we run it, our prediction on the test set is about 93%, and not too far from the prediction on the training set. Are we together up to that point? So now when we change the kernel, you can see the prediction is better. Previously, with the linear kernel, which was a wrong decision boundary, we were getting the wrong, our prediction was really bad. The accuracy was really bad. Now we are almost at 98%. So I think this changes because I didn't set the seed. This process is random, so you don't set the seed, you'll get slightly different results every time you run it. So you can do in your own time. I don't know if I've done cross-validation for this one. Maybe it's better. So this to get the optimal parameters, you need to do some tuning. So you need to initialize some of the values. So for the where am I getting this data from? I think it's the same, this same data that we generated. It's the one we are using. So to tune the model, there's this command tune.svm. That's the one you use. So you need the data itself, then you need the label. This one is just the label, and the rest of the specifications. But now the difference is the following. You have put different possible values for the cost, starting from 1/10. That's a cost of 0.1 to 110 squared. 10 squared is 100. So this will give you all these values for the cost. So gamma is also another parameter for tuning the model. When you're working with polynomials, I think gamma helps you to, you need to tune, you need a value for gamma that is optimal. Then you can also put some starting coefficients. These are the different values for the coefficients. So 0.11 and 10. What does coef man mean? The constant term, I think. I need to check that. But this is one of the parameters you need to tune. There's gamma, there's this coef, and cost. So you give it different values. Each of them has 3 different values. So it will check on all different combinations of this and give us the best, the one that has the best accuracy. So this one has built-in cross-validation. We have stored the results in this variable tune out. So we can pick out the best cost parameter, the best gamma parameter, and the best coefficient. So we can run that one by one. So it tells us for cost 0.1 seems to give us the best result. Gamma value of 10, and this coefficient of 0.1. These 3 parameters seem to be optimal. So now, since we know what they are, we can plug them into our model. So the ones we found to be the best, we can plug them into our model. Let's see if there's any, is there any use? Now, yeah, you can see the accuracy seems to have gone up. Of course, you will need to do some cross-validation over several rounds to get a better feel of this. But you can see the accuracy has gone up now because you have optimized you have tuned the parameters. So here, this is some sort of black box. It does the tuning for you. It compares, it tests for each of these combinations of parameters and gives you the best. So you just give it a range. If the range is if it's too big, the range, then it takes longer to run. This is optimal, not optimal. Like that. So is that making sense? You get the best parameters, then you plug them into the model, and now run the model with the tuned parameters. And you can see after that, we are getting a slightly better accuracy. We can try to plot the model and see. So this one is the one that is automatically done by R. If you plot the model on the training set, that's what you get. So you can see it has recovered the circle that we had created earlier as the boundary. It's been able to recover it. And this is what will happen when you're working with real data. When you're working with real data, this circle is you will not know where the boundary is. You will be trying to look for this boundary. So you'll have to try different kernels and so on. So there are situations where the boundary is also not so, it's not a polynomial, it's a bit complex. And in such cases, you could use the radial basis function, the RBF kernel. So for this, we are going to create another set with some complicated boundary. So I will draw, what is happening up there is creating the data. When you plot it, you can see the boundary is a bit complicated. You can see my graph. So
yes, yes, yeah.
The boundary looks like this infinity pattern, right? It's like an 8. So it's not quite a polynomial. It's a combination. So what we have done here basically is use two circles and picked all points that are within the two circles. We treated them as one class, and then everything outside the two circles is treated as a second class. So now the boundary is no longer linear, and it's not a polynomial as well. So if you try the polynomial kernel on this, it may not work very well. We can try that and see. So first of all, we split. We'll again, this library, I'd already called it. I don't have to recall it again. We split the data as usual into the training and testing set, 80%, 20%. So now we run the model. You see, on this, we try to see what happens if you try to run a linear kernel on this. As you can see, clearly the data is not linearly separable, but no harm. Let's just try and see what happens. And you can see the prediction again is not so good. You just have 57%. So linear will give you a bad result there. What happens if you plot this linear? You can see almost every vector is misclassified. Almost all the vectors are support vectors. Okay, so very few are correctly classified. Almost all these X's are the support vectors, which are usually either misclassified or within the margin. So that's bad for us. Let's try something different. This time, let's try a polynomial of degree 2 as the kernel. The boundary looks a bit like a polynomial, but it's not quite a polynomial. It's a bit complicated. So let's see what happens. Again, here you have a slightly improved accuracy. We have moved from 50s to 70s, but it's still not correct. We can why didn't I plot it here? Let's plot and see what happens. Plot. So now if we plot it, let's see what, okay. So you can see it cannot recover the exact, let's go back to the exact boundary. So the boundary was an 8 kind of, but even just assuming a polynomial of degree 2 still does not give us a good result. Doesn't recover the exact boundary. You can see there are a lot of support vectors and many vectors that are misclassified. So it just gives the boundary as one circle, but it was a figure 8 for the other one. But still we get a slightly better prediction. The accuracy is now 77%. It's a little better than the linear one. So there's one more basis function which we can consider, which is called the radial basis function, or the radial RBF kernel. So we try this with the, now this one just does cross validation. We can run the cross validation for the polynomial kernel and see what happens, whether we can get a good average. So the average accuracy is about 80%. Doesn't vary that much, but it's still just at 80%. So now, instead of using the polynomial, we're going to use the radial basis kernel when running the SVM. So if I change this now, you can see this is no longer polynomial, it's radial. So for radial, you don't need to specify the degree. You only need a degree if you're working the polynomial kernel. So you'll notice now the degree, the option for degree or the argument for degree is not included because it's not needed for this model or for the linear model. It's not needed. It's only needed when you're working with the polynomial kernel. I think there are other basis functions which you can use as well, but for now, I think we will just be happy with the radial, linear, and the polynomial kernels for our work. So we will do cross validation for the same data, but now the only change is the radial basis that we are using, a radial basis function as the kernel. What have I done wrong? Okay, now it has run. I missed something before. So still running, I think. So now you can see the average accuracy after running it 100 times is about 90%. Again, we have improved from 80 to 90 because now we are using the correct kernel to find the decision boundary. You can also tune. Let's see, can we improve it by tuning the, what do you call it? Tuning the parameters. So we give it a set of parameters, another set of values for the cost. So in this case, we just need the gamma and the cost. And when you tune it, it should give you the best. So we get the attributes that we need are the value for the cost and gamma. So those ones, this is how you extract them, right? So this is the best parameter from this run. It will give you the best parameter for cost, and this will pull out now the best parameter for cost from this run. So let's see if our accuracy will improve at all. Now we have moved to 97. After tuning the parameters, accuracy has really gone up. We are about 97% accuracy from 90 to 97. Now let's see what kind of boundary it produces. So you can see the boundary now is it's not quite exact, but closer to what we had before. It's not exactly circular. It goes like this and tries to make an 8 of some sort. It's much better than it's closer to the original one than when we use the polynomial. So maybe the only thing it gets wrong is somewhere around here where it's supposed to cut to make an 8. So just a little trouble here, but other than that, it gets the rest of the boundary almost correct, the decision boundary. And our prediction also is not so bad. We are at 97%. Now you can now run cross validation on this. So you can just do code like this, but now where you have SVM, you replace it with this one. You replace it with this one, run it 100 times and get the average accuracy over the 100 runs. So sasa mnaweza kutoa maoni. I think that is all for the class.
What happens if you use the radial kernel in the data that it follows a polynomial function?
You can try it and see.
Is it like I mean, is it generally something that is recommended or not recommended?
So radial basis. The reason it's called radial. Let me try to draw something here. It's I will share the board again. Where is the board? So the reason it's called radial is this. If I'll try to illustrate. So this case where we have used the radial, we have some points in here, right? And the others out. So the boundary is sort of radial. It's going out like that, right? So if you draw all these lines from some center, they seem to cut through the boundary. So this is how it's going to look for the boundary, going in all these different directions in a radial manner. So if you just have the polynomial, this will not be radial, right? So it may not be appropriate to use radial basis function when you have this kind of boundary. So the polynomial probably would be the ideal for this kind of boundary. And then the support vector machines are not the only things you can use. If you really have trouble, if you're very crazy in nonlinear boundaries, you may want to use neural networks. or some other algorithm. But the only issue is that neural networks are only useful if you have a lot of data. If your data is very little, then neural networks are not much help. But this is what it means, what radial basis means. It radiates out. So you can see the boundary is sort of radial. It expands as you go out. So but the best way for you to do this is to go and try it yourself. You can even create it's possible to create a polynomial boundary yourself. The same way I've created the linear one, I've created the circle. It's just basic mathematics creating the boundaries. You have one data set and then force a boundary on them. Then that becomes your decision boundary, and you see if so I did not create any polynomial boundary other than the circle itself. That's the only degree 2 polynomial boundary that we created. But this was also radial. I think if you apply the radial basis to this one, it will work. But also it's a polynomial because the circle is a polynomial of degree 2. So the polynomial will work. This other case that we were looking at is not a polynomial, but it can work with the radial basis. The radial basis will try to find that boundary sort of because it's going in all these directions and sort of searches for the boundary in a radial manner. So, but now the thing is, there are also other kernels. The challenge is for you to now go and do some extra reading on your own. There's no way you will ever learn everything in class. The class is supposed to get you started. You have to put in thousands of hours in this if you want to be a data scientist. It's not going to be something you will glance at and become a data scientist. There's no shortcut. If you just want to run the algorithms, that's different. But if you want to become a data scientist, you really must put in the midnight oil. What we are doing is not even barely close to what we should be doing. We have actually watered it down a lot because of a variety of issues. Not your fault. The fault is not yours, but we have to find the middle ground somewhere. But now, when you have something like this, it's important for you to read. And even there are some simplified videos online on support vector machines. Maybe now they'll make more sense. Sometimes when you watch them before seeing other demonstrations, they don't make sense. Maybe now they'll make more sense. Or not, I don't know. Depending on what my lesson look like. Oh, there's someone called Brian Kinaro here. Is there any chance this Brian Kinaro is related to Mr. Kinaro, who was a principal of Kisii High School some time back, a while back actually? And also was a headmaster for Kakamega High School when I was there. Brian does not talk. Okay. So